In this presentation, we look at selection of information to be used in a computer. Selection helps in communicating between and within the parts of the system. Circuits that perform selection typically have a set of inputs from which selections are made, a single output, and a set of control lines for making the selection. Let's begin by looking at multiplexers. A multiplexer is a combinational circuit that selects binary information from one of many input lines and directs the information to a single output line. The selection of a particular input line is controlled by a set of input variables. These are called selection inputs. Normally there are 2 to the n input lines and n selection inputs, whose bit combinations determine which input is selected. If this has left you a bit confused, here's a simpler definition of a multiplexer from your old pal Wikipedia. In electronics, a multiplexer, or mux, sometimes spelled as multiplexer, is also known as a data selector. It's a device that selects between several analog or digital signals and forwards it to a single output line. You can also think of a multiplexer as a way to select from many input streams in the same way that you would select a channel on your TV. Let's start with the simplest multiplexer. We begin with the 2 to 1 line multiplexer. The function has 2 information inputs, I0 and I1, and a single selection input S. Here you can see the truth table for the circuit. If the input S equals 0, the output of the multiplexer takes on the values of I0. If the select input S is equal to 1, the output of the multiplexer takes on the values of I1. So S selects either input I0 or I1 to appear as the output. Our equation is Y is equal to S naught I0 plus S I1. This same equation can be obtained by using a 3-variable K-map. The implementation of the preceding equation can be decomposed into a 1 to 2 line decoder, 2 enabling circuits, and a 2-input OR gate, which you can see in this figure. This implementation uses the idea of hierarchy of simpler circuits to build this more complex circuit. A common symbol for a 2 to 1 multiplexer is shown here. There's the trapezoid signifying the selection of the output on the short parallel side from among the 2 to the n information inputs that appear on the long parallel side. Now let's look at a slightly more complicated multiplexer. For a 4 to 1 line multiplexer, the function Y depends on 4 inputs, I0, I1, I2, and I3, and 2 select inputs, S1 and S0. The table on the slide shows a very condensed truth table for the multiplexer based on S1 and S0. Each row represents multiple rows for the full truth table. Since there are 6 variables and only S1 and S0 are fixed, the single row represents 16 rows of the corresponding full truth table. Here is the equation for the 4 to 1 line multiplexer. If this equation is implemented directly, 2 inverters, 4 3-input AND gates, and a 4-input OR gate are required. This gives a gate input cost of 18. In regard to the previous equation, we can factor the AND terms to get a different form of the equation that's a bit simpler. We can construct this one by combining a 2 to 4 line decoder, 4 AND gates used as enabling circuits, and a 4-input OR gate. The resulting circuit has a gate input cost of 22, which is more costly than our previous implementation of 18. Nevertheless, it provides a structural basis for constructing larger n to 2 to the n line multiplexers by expansion. Multiplexer is also called a data selector, since it selects from one of many information inputs and steers the binary information to the output line. The term multiplexer is often abbreviated MUX. Multiplexers can be expanded by considering vectors of input bits for larger values of n. Let's take a look at a 64 to 1 line multiplexer. Here we're designing a multiplexer for n is equal to 6. This means that we're going to require a 6 to 64 line decoder and 64 times 2 AND OR gate combination. Adding up all the gate input costs gives a total of 374. We can replace the enabling circuit decoder with inverters and 7 input AND gates. This gives a gate input cost of 518, which is larger though. To reduce the gate cost for a single bit multiplexer, we can combine the AND gate generating D sub I with the AND gate driven by D sub I into a single 3-bit AND gate to reduce the cost down to 310. This trick won't work for multiple bit multiplexers. Let's take a look at one of these multiple bit multiplexers though. A quad 4 to 1 line multiplexer has 2 selection inputs, and each information input is a vector of 4 inputs. The inputs are a vector, so the output Y also needs to be a 4-element vector. The implementation of this multiplexer requires a 2 to 4 line decoder and 4 4x2 AND OR gate combinations. The gate input cost here is 58. In contrast, if four 4-input multiplexers implemented with 3 input gates were placed side by side, the gate input cost would be 76. So by sharing the decoder, we reduce the gate input costs. Example 312 and 313 show how to implement a 4-to-1 line multiplexer using Verilog and Vhdl in case you're interested in looking at that. Let's skip over that and take a look at a practical example in the form of a home security system. A home security system has 15 sensors that detect open doors and windows. Each sensor produces a digital signal 0 when the window or door is closed and 1 when the window or door is opened. The control for the security system is a microcontroller with 8 digital input-output bits available. Each bit can be programmed to be either an input or an output. We want a circuit that repeatedly checks each of the 15 sensor values by connecting the sensor input to a microcontroller input-output that is programmed to be an input. The parts list you see here can be used, and we can use any number of each of these parts, but we want to minimize the number of parts and the number of microcontroller inputs and outputs. One possible solution is to use two 8-to-1 multiplexers, each connected to a microcontroller input. The two multiplexers handle 16 sensors and require 3 microcontroller outputs as selection inputs. Since there are 15 sensor outputs, the unused 16th multiplexer input can be attached to 0. The number of microcontroller inputs/outputs used is 3 plus 2 is equal to 5. Using other types of multiplexers will increase the number of microcontroller inputs, so the initial solution is the best. A decoder combined with an M/2 and/or gate implements a multiplexer. The decoder in the multiplexer generates the minterms of the selection inputs. The AND/OR gate provides enabling circuits that determine whether the minterms are attached to the OR gate with the information inputs used as enabling signals. If the input is 1, then the minterm is attached to the OR gate, and if the input is 0, the minterm is replaced by 0. Value fixing applied to the inputs provides a method for implementing a Boolean function of n variables with the multiplexer having n selection inputs and 2 n data inputs, 1 for each minterm. Furthermore, an m output function can be implemented by using value fixing on a multiplexer with m-bit information vectors instead of the individual bits. This is illustrated in the next example. The selection in this book covers some more examples, including a multiplexer implementation of binary adder along with an alternate implementation of it. There's also a multiplexer implementation of a 4-variable function and a 7-segment decoder implementation like you would see on old calculators. I will likely feature one of these on our homework assignment. Thanks so much for watching, and as always, be sure to check in on La Lima.